Hi, chemistry class. It is Wednesday, March 25th, 2020, 10 a.m. right now is when this is being posted. Welcome. Glad to see you guys. Glad to be back. So I'm just going to share my screen with you so that we can get this rolling. So you are going to be following along as usual starting on page 5 of your handout packet. So first and foremost, just want to make sure again that we have my contact information. This is all in the Google Classroom and then also in the link in the description. So if you have any questions, comments, concerns, I cannot stress this enough to reach out to me in some way. In a comment, email, text, call, if you'd rather do that. I'll try to get back to you in a timely manner. So today, again, we are focusing on the same standard that we did on Monday. So we talked about how temperature affects reactions. So we looked at the green food dye and how it moves through the hot versus the cold water. So we're going to be doing something similar to that today. We're going to talk about temperature and how 3 other factors affect reactions and what reactions are in general and how they change the reaction. So our objective for the day is I can describe what happens to concentration of reactants and products and energy in chemical reactions, as well as the factors that affect chemical reactions as demonstrated by performing activity and taking notes. So without further ado, we're going to start with on that first page on page 5. Think about a phenomenon that interests you. Write it down and why it's interesting to you. So I want to introduce this word into our vocabulary if we don't already have it. So a phenomenon is an observable fact or event. So it can be a solar eclipse. It can be like I have over here on the screen, the northern lights. That's a phenomenon. It's an observable fact or event. Another phenomenon is the citrus in the orange peel could cause a balloon to pop. So something observable. And so pause the video now. Tell me what this observable fact or event that you find really interesting and why. Okay, welcome back. You should have written down that first couple lines on page 5 of a phenomenon that you find interesting. So it can be anything that you find interesting, and comment them in the comments below so I can hear what you guys find interesting. So now we're going to start off with some notes. So typical as to when we're in class. So the underlined portions are what the notes are. So first and foremost, I want to show us that a chemical reaction goes from reactants, or sometimes they can be called reagents. So they're the things that are reacting to form, they form products in a chemical reaction. So products are something that we're being produced, and reactants are something that's reacting. So you can see on this concentration versus time curve, concentration is basically the amount of something that we have. So as the amount of reactants or reagents goes down, the amount of product goes up. And this should make sense because the reactants or reagents are turning into product. So you use those up to create more product. So as they're going to be having this indirect relationship. So you start with the concentration of reactants, so an amount of reactants, and this is going to decrease over time. And that should make sense. So as the reaction occurs, the products are formed from these reagents, the reactants getting used up. So this reaction occurs quickly at the beginning and then slows down. So you can see that the line here, it has a larger slope at the beginning, so a steeper slope and a less steep slope at the end for both products and reactants. So reactions start off quickly and then they start to slow down as there's less reactants to work with to form products. So at the molecular level, reactants interact, meaning they collide with one another. If these are strong enough collisions, the bonds of the reactants will break and a reaction occurs, which is going to form new bonds. An example of this is when 2 bromine nitrate forms 2 So when it forms 2NO plus bromine. Okay, I apologize for me messing up there. So you can see here, so these are reactants. They come together in a collision. So B shows the collision. These lines are meant to signify them crashing together. C is an activated complex, which is like a transition state, which shows them like forming this intermediate before they form the products. So they form this intermediate with each other before they break off with each other and form the products. Okay. Reactions, it's going to be a change in energy over time. So we already talked about reactions changing temperature over time, potentially. So there's endothermic versus exothermic. We talked about that a couple units ago. And now we're talking about change in energy over time. So when the reaction starts, T equals 0, and T here stands for time and not temperature. So time, so the amount of time that has elapsed since the beginning of the reaction. So when you first begin the reaction, your time is 0 because it's all relative to when the reaction began. So time equals 0 would be down here at the far left, bottom left-hand corner of the graph. So when time equals 0, there's only reactant with a certain amount of energy. So we're starting here. So reactant starts here on our reaction progress versus energy graph. Reaction is going to start here where the line starts. And this should make sense that there's only reactant because at time 0, the reaction hasn't even really started yet. So we have only reactant at this point. So reactants, as you know, must collide in a proper orientation, meaning they must fit together in a specific manner and with enough energy in order to make the reaction start. So if there's not enough energy or they collide not where there's going to be a reactant with each other, then there's going to be no reaction. This activation energy signified, this is supposed to be EA, E underscore A right here, so I apologize. You have it correct in your notes. So E underscore A is this minimal amount of energy required to make these atoms or molecules in such a state that they can begin a chemical reaction. So that is signified on our graph over here to the bottom right with this big bump. So it's called the bump. So by this big bump right here. So that's how much energy we need from down here to up here, this EA, in order to begin our reaction. So some reactions simply don't happen without outside help because it's so much energy to overcome. So the activated complex. So as a reaction progresses from the reactants to the products, which is the definition of a reaction, it goes through a transition state. We call this an activated complex. And this is how the molecules are arranged at the top of the energy barrier. So the transition state is this little bump here. So before our reactants form the products, they form that little complex that I showed you a couple slides ago where they're all connected to each other like this. So exactly like this. So these are how the chemicals or the molecules are arranged before they break off. So this is a high energy state, meaning it's highly unstable. So at the end of the reaction, there are products with a certain amount of energy. So they also lie on this energy. So you see that they also have a certain amount of energy. So this little graph thing should be something that you should be familiar with. So if you have any questions about it, please let me know. Okay, and let me just orient us so that we know where we need to be. So you guys at this point in time should be on the top of page 7. So pause the video as needed, pause me if you need to get back, or if I'm talking too fast, if you need, pause me as the notes are on the screen if you need those. Okay, so delta E, this little triangle here is a delta, it's a Greek letter delta, and it stands for change in. So delta E, E stands for energy. So we have delta E is the difference or the change in energy of the reactants and products. So we're looking back at our handy little progression of the reaction or time and energy diagram. So we said that the reactants lie on a certain amount of energy, our transition state lies on a certain amount of energy, and so do our products. So delta E is going to be change in the amount of energy in the products versus the amount of energy in the reactants. So it can be measured using this little space. So basically you're just subtracting the reactants energy from the products energy. So we're coming back to endothermic versus exothermic. So endothermic means that it's an absorption of energy. Remember, endo, like entering something. So we're absorbing energy, it's entering the system. So our products are going to have more energy than reactants, meaning that they're going to be higher on the graph. So our examples right here, we see that our energy of our products is higher than the energy of our reactants. An exothermic reaction, on the other hand, releases energy. So exiting, exothermic. So our products are going to have less energy than the reactants. So as you see on this graph here on the right, you see that the energy here has less for the products than the reactants. Okay, finally, so we're gonna see how fast products are formed or reactions are used by measuring the reaction rate. So that's the definition for a reaction rate. It's how fast products are formed or reactants are used. And there are 4 major factors that affect our reaction rate. So first is concentration, and this should make sense because the concentration is the amount of reactants we have, I'm sorry. So as this concentration of reactants goes up, there's gonna be more particles to collide with one another. So there's gonna be more collisions just based on statistics, and this causes our rate to increase. Temperature we talked about yesterday, on Monday. And so as temperature increases, our particles are moving faster because they have more kinetic energy. So more collisions occur, and thus the rate also increases. Our third example is surface area. So reactions take place on the surface of something. So as this just the surface increases, the surface size increases, the reaction rate is also going to increase because there's more space for reactions to occur, to collide with one another. And it's also important to notice that in all 3 of these examples, we're going to talk about a 4th one in just a second, all 3 of these examples are direct relationships. So as concentration, temperature, and surface area all go up, the reaction rate likewise is going to go up. So finally, our 4th and final major factor affecting reaction rates is a catalyst. So a catalyst is a substance that speeds up a reaction without being consumed. So it makes the reaction go faster without being used up like the reactants. So this, an example that should come to mind are enzymes. So in our body, we have specific proteins called enzymes that make reactions happen a lot faster than they normally would. So enzymes are actually really fundamental for life because a lot of reactions that we have in our body would take so long to happen on their own that if they didn't happen with the enzymes, we wouldn't be able to survive because it was such a slow pace. So catalysts lower this activation energy. So they make that bump smaller because they provide a new pathway for a reaction to occur. They can like align up the collision to be more beneficial and quicker. But it's important to note that they're not actually changing the energy of the product or the reactants, like the final energy of the products or the reactants. They are simply just making the bump smaller. So they're making the hill to climb over smaller, meaning the reaction is more likely to happen because it's going to require less energy. So here's a visual example, just way to look at it. So as you can see, the dotted line is the reaction without or with a catalyst, so with its extra help, and then the pink line is the line of the reaction without the catalyst. So as you can see, they both start and end with the same exact amount of energy. The only thing that is changing is the size of this bump. So the hill to climb over is smaller. Okay, so now it's time for you to pause the video and get thinking. So I know that was a lot for you guys to write down. So good job, proud of you for making this far. So on the on the top of page 8, you are going to begin filling in this question. So think back to the phenomenon that you thought of at the beginning of this video. So can you answer any of the questions or wonderings that you had? So why you found this interesting? Is there anything about what we talked about now that you know about reaction rates and what affect reactions? Does any of that change? So take some time now, pause me, take all the time you need to think about your phenomenon and how it relates to chemical reactions and what drives reactions. Welcome back. So you should have completed the top of page 8. And now we're going to move on to the final thing that we're going to do. So our big question, and this is the final question that you need to answer. So along with posting what phenomenon you found interesting in the comments, also post the answer to this question. So what factors are affecting the rate of reaction? What 4 factors did we just talk about? And why are they affecting the rate of the reaction? So why do each of those different factors affect a reaction? So do your best to do this out of memory, but if you need help, flip back in the video, flip back in your notes. So pause the video now to write this in your notes, and then copy and paste it and write it in the comments of this video. Okay, welcome back. So you should have completed the bottom of page 8 of your packet. So you should have up until page 8 completed for this week, at least. So now just a look ahead. We have our latest live session out yesterday at March 24th, 2020. So I solved some problems that are similar to what you need to do for Mini QPA 1. So if the final 2 math problems were giving you trouble on Mini QPA 1, I suggest you look at this live session. So go to Live Sessions Chemistry, the playlist, and then click on March 24th, 2020. And we're gonna go over 2 separate problems on there. We have another live session coming up tomorrow at March 26th at 10:30 a.m. Hope to see you there. And then a new uploaded video, final one for this week, is gonna be on Friday, March 27th at 10 a.m. So you guys made it to the end of the video. Congratulations, real proud of you, good job, keep up the good work. And as always, if you have any comments, emails, texts that you really need to send me, that you don't even really need to send me, I don't know why I said that. So if you have any comments at all, questions, concerns, please do not hesitate to comment on the video, comment on Google Classroom, email me, call me with all of your questions. So good job today, you guys. I'll see you next time. See you at the live meeting tomorrow.